All right, so second video in section 3.1, we're going to talk about increasing functions, decreasing functions, constant functions, at least in the context of lines or linear functions. Okay, so we're still talking about linear functions, which remember are functions of the form mx plus b. M is the slope, okay? If the slope is positive, then the function is increasing. If the slope is negative, the function is decreasing. And if the slope is 0, the function is called constant. In other words, the value will never change, the value is constant. Okay. So, looking at these, determine which of these linear functions are increasing, which are decreasing, and which are constant. Pause the video and just ask A, B, C, D, which ones are increasing, decreasing versus constant. Okay, so A, because the slope is 3, which is positive, it's increasing. For B, the slope is -6, which is negative, so it's decreasing. For C, the slope was positive, so it's increasing. For D, this is probably the most tricky one. Okay, we had h of z is 4. And a lot of people might look at this and say 4 is positive, therefore it's increasing. But remember, 4 is actually the intercept here. The slope is what is multiplying the variable, and it looks like it's not there, so it's actually there times 0. The slope is 0. You generally won't write 0 times variable, so this can be a little tricky to pick up at first. But if the variable isn't there, it's actually there times 0. So this is a constant function. In fact, for this function, h of z equals 4. If I plug in z equals 3, what do I get out? I get out 4, because what if I put a 0 in here, sorry, a z equals 0 in here, nothing changes. There's just the 4. So what's h of 0? 4. What's h of 10? 4. What's h of -8? 4. It's constantly 4. That's the reasoning behind calling them constant functions. Okay, so let's talk modeling. Okay, if I know I have a linear rate of change, a constant rate of change, so a linear function, then I can call that the slope m, and if I can compute a single point on this model, or maybe the intercept, then I can give it a linear function that represents it. Okay, and remember, b, in this way of writing mx plus b, b is the intercept. Okay, so an example. So if you have a company, the book value is something that sort of represents, it's the value of a particular asset. Okay, so sometimes things lose value over time. Like if you buy a car, even if you don't drive it at all, just because it gets older, it becomes less valuable. And you might represent this with a straight line depreciation, sorry. Okay. And this would mean I'm assuming that the depreciation is a linear model. I'm assuming that the rate of change of the value is constant, that the average rate of change stays the same. Okay, and that is saying that the value declines by the same amount every year. Okay. So suppose you've just purchased a fleet of new trucks at $35,000 each, okay, and you want to depreciate these assets over 7 years. And what this means is you want to assume that over the span of 7 years, the value goes down to 0. Perhaps in this company, you're assuming people are driving them a lot, and you think after 7 years, they're going to be worn out and no good. So you just want to know what they're worth at certain points in between. So you're going to depreciate them over 7 years. Okay. Well, if I want the value to go down by $35,000, but over 7 years, we want it to go down by $5,000 per year. So if I want the value to go down by $5,000 per year and to start at $35,000, can you come up with a function that models this, graph it, determine the value after 4 years, interpret what the slope means, and then answer the question, when will it be worth $10,000? Okay, so we know, just to re-summarize, it starts at $35,000, it goes down by $5,000 a year, and we want to do parts A, B, C, D, and E. So please pause the video, try to work this out, and then we'll come back and answer it. Okay, so let's take a look at the solution. Well, we know that at time 0, that should be the value at time 0. The value at time 0 should be $35,000. This tells me the y-intercept of the function. So if we're looking for y equals mx plus b, we now know that the intercept is 35,000. Okay. The depreciation is how the value is changing, but we want it to change by 5,000, and that's the slope, but we don't want it to be positive. We want the value to be decreasing. We want the slope to be negative. So the slope should actually be negative 5,000. So now we have m is negative 5,000. And now that we have m and we have b, we have the linear model. Okay? So v of x is negative 5,000x plus 35,000. So this right here tells me it is decreasing at a rate of $5,000 per year. And this right here tells me it starts at a value of 35,000. So here's a graph, okay? It starts at this intercept. After 0 years, it's worth $35,000. And then it goes down to a value after 7 years of $0. And I connect them with a straight line. So what's the value after 4 years? Well, we've got this model right here. So all we have to do is plug x equals 4, because we're looking at 4 years, into this, and with $15,000. So after 4 years, we can kind of presume the trucks are worth $15,000. So part D was, what does the slope represent? The slope is the average rate of change. Negative 5,000, its value goes down by $5,000 per year. Okay, so every time a year advances, the value of the truck goes down by 5,000. Okay. And then the last question said, when will it be worth 10,000? So 10,000 is not what I'm plugging in. Remember, x represented years, and v was value. And that was the function v of x. So now we know we want the value to be 10,000. Okay, a very common mistake is just to see the number 10,000 and say, so I plug it in for x. But we're not trying to determine what the truck is worth 10,000 years from now. We're trying to determine when is the truck worth 10,000. Okay, so if I let that be v of x, now we can solve for x. So what's the first thing you do here? Well, there's several options, but probably we're going to subtract 35,000 to each side. And now we'll divide by negative 5,000 and get x equals 5. So at 5 years in time is when the book value of the truck will be $10,000. Sometimes people ask, why would a company be interested in what the truck is worth? Like, they just buy the truck and then maybe use it until it's worn out and they have to replace it. What does it really matter in the interim? Honestly, it has a lot to do with taxes. You may have to pay taxes based on what something is worth. And if you can sort of use accounting rules like this to say, well, I bought the truck for $35,000, but that was 2 years ago. Now it's only worth $25,000. You can pay less tax on it. Of course, consult an accountant or become an accountant. You have to do this in a legal way. You can't just claim stuff is worth whatever you want. But this sort of bookkeeping is quite important. Okay, so another example. Supply and demand. So we have quantity supplied. That's how much a company can produce. And quantity demanded is how much people actually want, given a certain price. So we'll call the supply S and the demand D. So here are just some variable names, supply and demand. Hopefully we can keep that straight, of cell phones. And here are two different functions. So P, is the price. Okay. If I charge a certain amount, okay, here is how many I can produce for sale. And here is how many people will actually want to buy. The equilibrium price is where supply equals demand. If the supply was higher than demand, you'd be producing phones that aren't being sold. If the demand is higher than supply, then people want to buy it, but they can't because there isn't anything there. You might be interested in a nice equilibrium. What is a price at which producing the phones and selling them is exactly balanced out? Okay. Can you determine what prices supply will be bigger than demand? Can you graph the two and label the equilibrium point? Okay, so, sorry, here are the three questions. The slides that are provided don't actually put the functions on this page. Okay, find the equilibrium price. Where are the two functions equal? Can you plot them? Can you determine where one is bigger than the other? And just to go back to the previous slide, here are the two functions. Okay, 25p minus 680 is supply. Negative 7p plus 3000 is demand. So each of these individual is a linear model. I have two different models, sorry. I have two different linear models in this problem, 25p minus 680 for supply, negative 7p plus 3000 for demand. So can we find where they are equal, where one is bigger than the other, and then graph them? So pause here, try to do this. Okay, so if I set supply equal to demand, okay, I just take my two models, supply equals demand. Now, if we add 680 to both sides, we'll end up here. Now I'm going to add 7p to both sides, and we end up here. Divide by 32. This is just 3,680 over 32, and we get the price is 115. So if we charge $115 per cell phone, the amount produced will match the amount that people want to buy. Okay, so to find what that quantity is at this price, you can just take that price and plug it into either. Remember, they should be equal, so it shouldn't matter which one we plug it into. So just for the sake of argument, if I plug it into supply, the price is 115, and remember supply was 25p minus 680, and we'll just compute 2,195. So if I produce 2,195 cell phones, we should be at equilibrium. Now if I want to solve where is one bigger than the other, instead of setting them equal, I say supply is bigger than demand. We go through the same steps, and now I divide by 32. And I just want to caution you, when you divide an inequality, always ask, are we dividing by a negative number? If you divide by a negative number, remember you have to flip the inequality. In this example, we divided by 32, which is not negative, so we do not have to flip the inequality. So if we charge more than $115 for phone, what we'll have done is we'll have suppressed demand enough that people aren't going to want to buy the phones, and we'll have extra supply. Here are the two functions graphed individually. Okay, notice that demand is going down. Demand is decreasing while supply is going up. If I charge more for a phone, manufacturers are going to want to make more of them. Okay, but people are going to want to buy fewer of them. So supply will go up, but demand will go down. Okay, so that's the end of this section. So come on back for section 3.2.